Literal equations. Literal equations, if you look at it, it looks like literature or literary, stuff like that. It has nothing to do with throwing garbage on the ground, but it does have to do with letters. That's where literal comes from. I used to say that someone that studied a lot was, back then in the 1700s, a man of letters. Someone that was literary, someone that had a lot to do with letters. The concept of literal and letters coming together works really well here because formulas can be viewed as literal equations. Because they have more than one letter in them. So when you see a lot of letters, you shouldn't automatically say, oh no, too many letters for me, this is a math class. You should say, okay, what can algebra tell me to do with the letters to get to where I want to go? And that's what solving any problem is about, getting to where you want to go. So even if it's a bunch of letters that are involved in there, let's work on isolating the variable. But we have some good news. If I give you 42 over negative 7, it is your job, by being in a math class, to be able to get that as negative 6. If I give you negative q over r, you don't have any more responsibility because you don't know what negative q is, you don't know what r is. You leave them as the letters. So, when there are letters in our literal equations, they will almost always all still be there at the end of our isolating of a different variable. This is why it comes with equations, because it's about isolating the variable that we need. What will happen is you'll have an equation, and the thing you need to know will be buried in the middle of the equation. And you know all the other variables, and you can put in the numbers and then do some arithmetic and try and work its way out with algebra and get it done. But what we do with literal equations is we move them as letters, and we get them to take us to the point where we have isolated the variable we need to solve, and now we've created a useful formula for that customer who wants to know only one number, and that customer is only capable of arithmetic. That's the goal. So think of yourselves as stronger than the customer who's paying you to isolate a variable when there's more than one letter in the equation. Now, if they can't do algebra, they might not even be able to do it very well with one letter in the equation. We're going to handle it with lots of letters. Literal equations have several variables. Several means generally more than one, right? One isn't going to work for us, but several could be many or could be two. We'll see. Variables are letters and need us to isolate one specific variable. Someone can't just give you a formula and say, okay, go. They either have to give you all of the numbers except for one, the values for each variable, and ask you to go find the missing one, or tell you which variable to isolate. And that's what literal equation work we're going to do, is isolating the variable. So, do the inverse operation. Right? We want to do the inverse impact that we did in equations. We want to get them to wipe out the work that's in the way of us having the right variable isolated, even though they're letters instead of numbers, right? 5 minus 7, going to get us to 5 plus negative 7, get negative 2, see where that takes us. A minus B is A minus B, and it stays that way, and people have to live with the letters. Do the inverse operation on both sides of the equal sign. To make the interference go away. Now, it will show up sometimes on the other side, right? That's what happens. We gotta get the interference away. The impact is moved over to still have the outcome based on the same reality, but it's on the other side. So this gets a little weird when there's so many letters. We do this until our variable, the one we're looking for, is isolated, and once it's isolated, it's going to stand alone. 1. The steps. There are, as I see it, in this type of level of literal equation plus the next level of difficulty. There are 4 steps in order that you'll do. The third step is one that you won't be able to handle in this class, but it will come in handy for you to do a literal equation work in the next class after you learn factoring in Math 136 to handle a really difficult problem. So I'm going to put that in there, but I'm going to put a star next to it and say this pretty much happens in the tougher problems, and we'll only have 3 steps to go with. But number 1 is clear fractions. If there are no fractions, you get to skip that step, but this is where you multiply by the LCD of all your terms, cancel away all the denominators, and now you're looking at no more fractions in the work. Number 2, undo any addition or subtraction. To get all terms of the sought variable, the variable you're looking for, the variable they have to tell you which one to go get, on one side of the equals. Switching to blue for step 3 and putting a star before it even gets started, because as a student in this class and setting of Math 094 at Normal Community College, we don't know how to factor yet. We don't guarantee you know how. Maybe you do, and then you can do this one, and you can do the hard ones, because you brought that knowledge in with you. But I haven't taught you how to factor, and I won't in this class. You'll learn it in 136. But I'll put out here, and of course it's implied that it's if needed, so it won't be needed in our class. But if you're in a 136 class, it very well might be needed to have you factor out the sought variable as the GCF. And once you learn how to factor out the GCF, you'll know what factoring is more so then, and you'll have an understanding of why we do this. But then comes back to this step. So we will go 1, 2, 4. I know. When we do our work, we'll look about 1 to see if we need it. We'll get to number 2, and then we'll go to number 4. Use division, or occasionally multiplying by reciprocal, but I'll call it division, to isolate the variable. That's how we do it. General recipe, in order, right? Recipes should be done in order. And we'll take them through the process to get to our isolated variable. So I'm going to leave the steps up there as we look at how we're going to isolate variables here with our literal equations. And then I'll have a pretty sizable isolation homework 10A. We'll do a good job of isolating variables in a lot of different scenarios, but right now we're looking at understanding what are the things I'm supposed to do even though I don't know how to do step 3, so it's the teacher's job to make sure not to give me a problem in Math 94 that requires a step only taught in Math 136, of course, after this. So let's try this one. It says solve for x when it's got x minus y equals 5. This is a really important one, and it'll come up again in the third and final one that I do in this demonstration for you. So we want to solve it for x. Let's see what we got here. We have an x, we have a dash, we have a y, then we have equals, and then we have a 5. What do we have, and how are we going to work with it? I'm going to plus negative y. Let's see. How many y's? You're right. Ones. Behind the dash is 1, in front of that is 1. So now what have we come up with? This equation has become a little bit more workable because coefficients are now visible. When I see this as 1x plus negative 1y equals 5. Sorry, let me leave space in front of the 5. If you've ever heard y equals mx plus a letter, and I often ask the class what letter, and someone out of the group will say B. I'll say, great. Some of you have done this a little bit before, maybe a lot. You want the y to be first, the equals to be second, then the x term to be third, finally the number that has no letters on it last. Which is why, from the time we start doing this, if we're isolating y, I try to have it be y first, then equals, then the x term, and then the number. That's why there's space in front of my 5. Because what I'm about to do here is get the x alone. I'm going to add one y to both sides, and I have my number last. And I like to finish with the number. It's kind of like a period at the end of a sentence, and an expression that often it will end when you have what we call a polynomial. It will end with the number if you have one. This is going to be 1x equals 1y plus 5, because I did addition here. Or, so I said y, how about y? Commonly known as x equals y plus 5. If I put a 2 in for y, x will be 7. 2 there, right? 2 plus 5 gets me 7. I'll know x is 7 if y is 2. 7 minus 2 gets me 5. The same relationship is maintained. But now I'm able to find x when someone gives me a y, or your customer can only do arithmetic. And they want to know, how am I going to find x if I know y? You give them this literal equation that literally does the job for them if they can do arithmetic. So that's the first of these. Now I want to get one that's a little bit crazier looking, but follows the same rules. And then I want to get to the most important kind of isolation that you will deal with in this course over and over again as we go into further work on graphing lines and things like that. We're going to solve for x again. That one had 2 variables, the one we just did. Get ready. mx plus ny equals r. How many letters? 1, 2, 3, 4, 5. That's not a T. 5 letters. There could be many. There are several. Right, here we go. We want to solve this thing for x. So I have mx, I have plus, I have ny, I have equals, and I have r. I'm going to put my 1's in for each coefficient. So now I have 1mx plus 1ny equals 1r. Undo any addition or subtraction. So use plus or minus so that you get the terms that involve x on the side by themselves. Here's the x term, so that's going to stay. This plus 1ny has to go, so that the x term is on the left, and it's the only one, it turns out, here, and the other side has all the things that don't have x in their terms. So subtract 1ny. Unchanged 1mx, cancel to 0 and don't write it, equals 1r plus negative 1ny. And I'll pop that up here. 1mx equals 1r plus negative 1ny. And now what I want to do is get x alone. So I don't want to have the 1 or the m in front of it, although the 1 in front of it doesn't cause any harm. I want to divide each term here so that I only have the x left. So I want to divide this by 1 and m. I want to divide this by 1 and m. I want to divide this by 1 and m. And when the 1's cancel and the m's cancel, I have nothing here but x. Perfect. Now I'm ready to see what else it leaves me. 1r over 1m plus negative 1. On the top I have ny, and on the bottom I have 1m. What does that mean? That's going to mean that x equals, if I don't put the 1's, r over m plus negative ny over m. Does that look better? Probably not. Does that look worse? A lot of you will say yes. But x is isolated, so when our customer says, I know all the letters and I'm awesome at arithmetic, or I have a calculator, but I can't get that x out of the mess that it's in. When it's in here, we just did it. Quick look at what else might happen if you have your mx equals r minus ny, is some people will say, just divide by m, but put this in parentheses, or put it as r minus ny all over the same m. Those are acceptable. So I leave it there if that's what you want to do, but I do prefer and find benefit to doing the case where I divide each term on the other side by my coefficient that I'm dividing by. So now if you know values for r, n, y, and m, you can put them in this formula or that formula and get your value for x. If you don't have the isolation, you got to put all the variables in there, get the numbers, see what they create, deal with the algebra to still get the numbers to do some work before you've isolated the x with the numbers there. This will work. Strictly doing arithmetic will get us through there. Now, the most important kind. It's not exactly like the first one, and it's not, luckily, like this one I'm just erasing now. The most important kind is for you to be able to isolate y in an equation involving y and x. I had said about y equals mx, and someone in the class always, and in this virtual class, I'm imagining someone shouts out plus b. Great, it's got the letter y and the letter x. M is the slope, and then b is the y-intercepts y variable. Okay, y value, really. The idea there is x and y are the numbers that we use when we graph a line. And that's coming up for our third exam. And it is far more important that you get used to isolating y than isolating x. So, we're going to learn how to isolate y by following these same kinds of ideas here. We have 3x minus 7y equals 14. And I could ask you to isolate y. There's nothing illegal or wrong about that. But the useful values that we get, useful formulas that we create, are when we isolate y. Because one of your classmates would recognize y equals, and then comes the rest, mx plus b, that has an x involved and some numbers. So I'm going to isolate y here. So I'm going to write my 3x plus negative 7y equals 14. Now, the way I tend to do that is when I write the 14, I know I want y, then equals, then the x term, and then the number term. So I'm going to put my 14 over here, just so I have columns available for like terms and such. I want the y alone, I need to get the y term alone, which is negative 7y. That means I'm using addition or subtraction to get this gone. Negative 3x, negative 3x. We're doing addition here, and that's gone. Negative 7y equals negative 3x plus the 14. Up here we have negative 7y is negative 3x plus the 14. Now we're not done because I didn't say isolate negative 7y. If I did, you would be done, but no, I need to isolate plain old 1y. Now what's going on between the 7 and the y? It is not subtraction, it is multiplication, and it is negative 7 that is multiplied by y. So what do we have to do? We take our negative 7y, is negative 3x plus 14, and we divide each term by negative 7. And when we go back to see what we've created, we're going to reduce each term as much as we can. The opposite of negative is positive, right? 2 dashes. 7 over 7 is 1, which is why this gives us y equals. The opposite of negative is positive. 3 over 7 doesn't reduce. X is in the numerator. It could be 3x over 7, or it can be 3 over 7 times x over 1. I don't need to write the over 1 when we're looking at that. Plus single negative from 14 over 7. 14 divided by 7 is 2. I'm not as certain that I get this out of every class, but I sometimes do. So I'll say, what we call the 3/7, and a fraction is true, but not good enough for what we're looking for here. What we're looking for here is, that's the slope. That's the slope of a line. We'll see it later. But the reason we want to do y equals x term plus number is this will tell me y equals slope x plus intercept. That's the y coordinate of the y-intercept. That would be very helpful when it comes time to graph it. Anyone that's graphed it before successfully and remembers it, which is a lot, knows that if you put in 0, you get the point 0, negative 2, which you can graph on graph paper. And from there, you can go up 3 and right 7 to get a second point, and 2 points will help us draw the path of a line. So isolating y, if I wanted to graph this line, I could graph that line, but that line is more ready for me to get to work on it. And there's a lot coming with the red and green, but I call it y equals slope x plus intercept, where that is the y coordinate of the y-intercept. And so isolating y is a very big deal, so I put several of those in the homework quizzes and stuff like that we have to do, because when you get this and I ask you to graph it, and then you might be a person who would turn to me and say, I can graph the y equals ones, but I can't graph the ones that look like that. It's strictly because you're not successfully isolating y, which we're trying to work on starting today. If you're good at isolating y, then you'll face this and you'll need to recognize the need to isolate y, but you'll have mastered the skill that gets you here, and then we can get to work on what's got to happen. But if you don't learn how to isolate y very soon, when we get to this, you might be like, oh, I can do those, but that one's too hard because the y is not isolated. So I need you to learn how to isolate y, and you'll see some of that in your homework. So that's our 10A.